Imagine a perfectly ordinary Tuesday. You wake up, check your phone, and make some coffee. The world outside is just as it always is. Cars are moving, planes are flying, and the internet is buzzing with news and messages. Everything seems normal. But 93 million miles away, something extraordinary is happening. On the surface of our sun, a vast, tangled web of magnetic energy has reached its breaking point. It unleashes a colossal explosion, a flash of light so brilliant it outshines the entire star for a few minutes. This is a superflare, an event of unimaginable scale, and it is aimed directly at Earth. You wouldn't know it at first. The light from the flare reaches us in just over 8 minutes, but its most dangerous component is a massive cloud of charged particles. This cloud, called a coronal mass ejection, travels a little slower. It takes a day or two to cross the void between the sun and our planet. Scientists at space weather agencies would see it coming. Alarms would ring, and warnings would be sent out across the globe. But what could we really do? What is this terrifying force of nature? A superflare is not just a bigger version of a normal solar flare. It is an eruption on a completely different scale, releasing thousands of times more energy. Think of a standard solar flare as a firecracker. A superflare, in comparison, is like a hydrogen bomb. To truly grasp the threat of a superflare, we must first understand the nature of the sun itself. Our star is not a calm, unchanging ball of fire in the sky. It is a dynamic and turbulent sphere of superheated gas called plasma. This movement of charged plasma creates immensely powerful magnetic fields. These fields are like giant invisible rubber bands, twisting and stretching across the solar surface, storing up vast quantities of potential energy. When these magnetic field lines snap, they reconnect in a new, simpler configuration. This process, known as magnetic reconnection, happens with explosive speed. This is the moment a solar flare is born. The same magnetic explosion can also hurl a vast cloud of solar plasma out into space. This is a coronal mass ejection, or CME. Think of it as a solar tsunami, a billion-ton blob of protons and electrons racing through the solar system at millions of miles per hour. The most powerful solar flare ever recorded in modern history was the Carrington event of 1859. Scientists estimate it was an X-45 class flare, a monster far beyond the typical X-flares we see today. It was so powerful that it set telegraph offices on fire and produced auroras that were seen as far south as Cuba and Hawaii. In the 19th century, its impact was limited because the world's electrical infrastructure was minimal. If a Carrington-level event happened today, the consequences would be catastrophic. To understand the true potential of our star, we cannot just look at what it is doing today. We must become cosmic archaeologists, digging into the past to find evidence of giant solar storms that struck our planet long before we had satellites to record them. By drilling down, we can travel back in time, analyzing the chemistry of the ice, layer by layer. We are looking for something specific, a sudden spike in certain types of radioactive isotopes. These are rare atoms created when high-energy particles from space smash into our atmosphere, a telltale signature of a massive solar event. One of the most significant discoveries in this field came in 2012. A team of Japanese researchers studying ancient cedar trees made a startling find. They found a sudden, unprecedented spike in carbon-14 around the year 774 AD. This spike was enormous. It represented a 20-fold increase in cosmic ray intensity compared to a normal solar storm. The 774 AD event was almost certainly a massive solar proton event, the result of a superflare. While Earth's archives give us clues about our sun's past, another crucial piece of the puzzle comes from looking outwards at other stars. Thanks to space telescopes like NASA's Kepler mission, we can now monitor hundreds of thousands of stars at once. Astronomers began to sift through this data, specifically looking for sudden, dramatic increases in brightness. They found them. On many stars, they observed flares that were hundreds or even thousands of times more powerful than any flare ever recorded from our sun. The breakthrough came when scientists focused their search on stars that were almost identical twins of our sun. They looked at G-type main sequence stars with similar temperatures, sizes, and rotation periods. The results were sobering. Even on these solar twins, superflares were observed. The data showed that a star like our Sun could indeed produce flares releasing 100 to 1,000 times the energy of the Carrington event. The astronomical observations confirmed what the geological records on Earth were telling us. Imagine the moment the Super CME arrives. It would be an invisible, silent impact. There would be no sound, no tremor, just a profound disturbance in the Earth's magnetic field. The first and most devastating consequence would be the collapse of our electrical power grids. The rapidly shifting magnetic field would induce powerful, uncontrolled electrical currents in the long transmission lines that span our continents. These rogue currents would flow into the thousands of high-voltage transformers that form the backbone of our power grids. The result would be catastrophic failure. Some transformers would trip offline trying to protect themselves. Others would physically melt down or even explode. This wouldn't be a simple blackout. It would be the systematic destruction of the most critical components of our electrical infrastructure. Unlike a typical power outage that might last a few hours or days, a failure on this scale would be permanent. High above us, in the silent vacuum of space, our orbital infrastructure would be fighting a losing battle. A superflare would be a satellite apocalypse. The intense wave of energetic particles from the solar storm would bombard these delicate electronic systems, causing widespread and irreversible damage. The first to fail would be our navigation systems. The GPS network, which we rely on for everything from driving directions to precision farming and synchronizing financial networks, would become unreliable and then go dark. Back on the darkened surface of the Earth, the secondary effects would begin to multiply. The loss of electricity would not just mean no lights or television, it would mean the failure of every system that depends on it. First and foremost, the water supply. The food supply chain would be next to break, but the most immediate problem would be refrigeration. Supermarkets and homes would lose the ability to keep food from spoiling. Within days, vast quantities of food would be lost. Commerce and finance would cease to exist. Electronic banking would be impossible. Credit cards would be useless pieces of plastic. The global financial system would simply evaporate. Without a functioning economy, people would be unable to go to work. Society would face mass unemployment and a complete breakdown of the economic order. Maintaining law and order would become a monumental challenge. Hospitals would be overwhelmed. They would struggle to care for patients who rely on powered medical devices. As resources become scarce, social unrest would be almost inevitable. Governments would struggle to coordinate a response in a world without power or communication, facing a crisis on a scale for which no one has ever truly planned. The impact of a superflare would extend beyond human society and into the natural world itself. The massive bombardment of solar particles would have a significant effect on the chemistry of our atmosphere. The most immediate concern would be the depletion of the ozone layer. This increase in UV radiation would have serious consequences for life on Earth. Phytoplankton in the oceans, which form the base of the marine food web, are highly sensitive to UV radiation. A significant die-off could cause a collapse throughout the entire marine ecosystem. The superflare would also trigger a technological disaster with long-lasting environmental consequences. The simultaneous burnout of thousands of large power transformers would release toxic chemicals into the environment. Furthermore, the breakdown of industrial facilities, including nuclear power plants that rely on electricity for their cooling systems, would pose a grave risk, raising the specter of multiple Fukushima-style meltdowns around the globe. Faced with such a colossal threat, it is easy to feel helpless. But humanity is not sitting idly by, just waiting for disaster to strike. All around the world and even high above it, a dedicated community of scientists and engineers is working tirelessly to give us a fighting chance. Our first line of defense is knowledge. These solar observatories are our sentinels in space, providing us with the crucial early warning we would need to prepare for a major storm. Space weather prediction centers spring into action, analyzing data and issuing alerts to governments, power grid operators, satellite companies, and airlines. An early warning is only useful if you can actually do something with it. The focus is on protecting the most vulnerable parts of our infrastructure, primarily the electrical grid. Engineers have developed devices that can block or neutralize these harmful currents. For our assets in space, the options are more limited. When a major solar storm is imminent, satellite operators can attempt to put their spacecraft into a safe mode, shutting down non-essential and sensitive electronic systems. The ultimate goal is to improve our predictive capabilities. The holy grail of space weather forecasting is to predict a major flare before it happens, giving us not days, but perhaps a week of warning. Scientists are using artificial intelligence and machine learning, feeding it decades of solar observation data. A key proposal is to place a monitoring satellite at a location known as Lagrange Point 5, or L5. From the L5 vantage point, we could see and characterize sunspot regions days before they rotate into a position where they could threaten Earth. However, science and technology alone are not enough. Effective preparation requires policy and international cooperation. A superflare is a global problem that does not respect national borders. This necessitates international agreements on grid hardening standards, data sharing protocols, and coordinated response plans. Governments need to treat the threat of severe space weather with the same seriousness they apply to other major natural disasters. This means creating national risk registers, funding resilience measures, and educating the public. We have explored the awesome and terrifying power of our own star. The sun is the giver of life, the engine of our climate, and the source of all the energy that sustains us. Yet this same star holds the potential for immense destruction. It is a double-edged sword, a cosmic entity that both nurtures and threatens its planetary family. This duality lies at the heart of our modern predicament. Our journey through the science of superflares reveals a profound truth about our place in the universe. We live in a cosmos that is not always benign. The evidence from tree rings, ice cores, and distant stars tells an unambiguous story. Our sun is capable of storms far more violent than anything our technological society has ever experienced. The 1,000-year storm is not a myth or a worst-case fantasy. It is a recurring feature of our star's behavior. We have simply been fortunate to live through a period of relative calm. This knowledge forces us to reconsider our relationship with the sun. The story of a superflare is ultimately a story about ourselves. Building a resilient civilization is a shared responsibility, a project for all of humanity to ensure that our technological marvel does not become our downfall. By embracing the challenge of space weather, we are not just protecting our power grids, we are safeguarding the continuity of human progress. Our future under the sun is what we choose to make it. We can choose to be a society that understands its environment, respects its power, and takes prudent steps to secure its own future. We are safeguarding the continuity of human progress and ensuring that our bright technological civilization continues to shine.